So good afternoon, everyone. This is lecture number 19, Digital MOS LSI Circuits E524. Yeah, so we were talking about a chapter called Static and Dynamic Logic Gates. So we have studied one part of static gate, which is CMOS static logic gates. So we learn through two facts that you are going to make the power up network and power down network. Other than that, we also learn the designing issues related to this CMOS logic gates, or how to design them with the ratio, right? And third part, what we have learned was logical effort. So the logical effort will compute the delay of stage. So delay of the stage can be found out, and that's D equal to F plus small d equal to small f plus p, where the small letters indicates that all these are stage delay, stage effort, and the parasitic delay of the particular logic gate. However, if we are interested in finding out the stage delay, it's going to be equal to n times GBH raised to 1 by n plus p, where this is nothing but multiplication of all parasitic delays. N are the number of stages, G is the logical effort, but the capital G is multiplication of all respective logical efforts. B is the branch effort, where B is nothing but multiplication of all such branches, and H is the electrical effort, which is C out path divided by C in path, and this branch BI is nothing but C off path plus C on path divided by C on path, right? So this is the thing we have learned in past few lectures. However, this chapter has not been yet over. This first part we have studied from Rabe book. This part we have studied from West and Harris. And now the rest of the topic under this chapter only has to be understood. So some of the static gates are still left, and thereafter we are going to move to dynamic logic gates, and then we'll conclude the entire chapter. So let's start with the next topic of the chapter 6 from Rabe. So I am following only one book for this entire chapter, which is Rabe. So I have not written here 6.21.1 is nothing but the CMOS logic gate, which we have learned through the CMOS technique, where power up and power down network were there. So we have learned already, and other than that, logical effort was also studied, but from different book, but that is also given in this book also. Okay, so if you want to follow Rabe, you can follow Rabe. If you want to follow West and Harris, you can follow that also. But like my lecture is on the basis of West and Harris. Now we'll go to the next level, which is assured logic and pass transistor logic. Our main agenda is to make sure that we'll make smaller area, very high speed, or you can say that the propagation delay are as low as possible, right? So all these things we want to have it, and on top of that, which I have not talked, power consumption has to be as low as possible. Notably, two kinds of power consumptions are there. One is static and one is dynamic. In the case of static, we'll have the static power consumption when both the transistors are on, and you can find out that by VDD. Or in the case of dynamic, it's coming from the changing of inputs, and by looking at the output you can find out the power consumption, which is dynamic. But notably, the power consumption is nothing but CL times VDD square if it is a static one, and if it is a dynamic one, it's equal to CL times VDD times F. I should say that delta F, right? So that we already studied from a CMOS inverter. So all these things we also studied. Now we are going to start with the different topics on static CMOS design. Let's start with the ratioed logic. So in the case of the CMOS network, where we were using the power up and power down network, where the complementary CMOS technique was used, one was connecting to VDD and one was connected to ground, and those were defined as power up and power down network. You need to keep the ratio between them just to make sure that the TPHL and TPLH are same. Along with that, you also wanted to have V in equal to VDD by 2. At the same time, you are expecting to have the V out is equal to also VDD by 2. So in that case, you need to make the ratio such a way that both the resistances are equal. But the next one is also the ratioed one, where ratioed logic is an attempt to reduce the number of transistors required to implement a logic function. Now, if you remember this logic, so as many number of PMOS transistors were there, number of PMOS transistors, same number of NMOS transistors, you have seen it, right? So the power up network and power down network will have equal number of resistances, with maybe you can say that the upside, which is power up network, you can have multiplication of 2 in the case of West and Harris. In the case of Rabe, he is using 3. So you can use some numbers so that you have the equal resistances, and because of that you can have TPHL and TPLH equal, and you can also control the value of VM, which is a switching threshold. So this is what you wanted to have it. And in this case, what we are proposing, that we will have lesser number of transistors. So this is what this technique says, that we will have the less number of transistors to implement a given logic. And when you are doing this, you may have the reduced robustness and the extra power dissipation. Means maybe like you cannot achieve the required NMH or NML, which is the noise margin. You may have extra power consumption. So those things will happen. But when you are looking into the circuit, actually the number of transistors will be reduced, or same number of PMOS transistor will not be there, as many number of NMOS will be there. So those things are categorized under the different logic, which is known as the ratioed logic. In ratioed logic, the entire PUN, which is the power up network, is going to be replaced with a single unconditional load. What exactly this meant to say is as follows. If you understand that, look, if I'm interested in finding out the inverter, I cannot make inverter just using this technique. Look, if I'm giving this input, output is exactly opposite of that, right? With the ratio of M1 and M2. What if I am doing, instead of this, if I am doing this, look, first of all, these signals are, what we are applying is large signal. This is a common source amplifier with some load resistance. With having enough gain, you can achieve VDD and 0, no problem, right? And it's exactly opposite will be available here. So this is also inverter, but it's a different class of inverter. But we are not going into that, like class A, B, and all these inverters name. But all the common source amplifier with different load, you can have, the characteristic what you are achieving here. In this case, same characteristic you can achieve here, same characteristic you can achieve here also. If I am using the current as a load, let's assume that this is V bias and this is V in, which is square wave. So the output will be inverted one, right? You can make it even like this also, which is diode connected. So that is what this sentence is all about. It says that it's a single unconditional device load which you are going to keep. It might be resistive, it might be like sometimes people are keeping diode also. So as such, this particular subject is talking about CMOS logic. So we are not going into that, but there are many other techniques like RTL, DTL. All these techniques are there through which you can design the logic gates like resistive transistor logic and diode transistor logic. So that way you can make that. So that we have kept it way behind in the previous course called digital electronics, which is undergraduate level course, which everybody have studied under the chapter called digital IC logic families. So in that case, you can use various loads. So this is again saying that you can use some load. It might be resistive, might be diode, and all other things will be here. So if you want to make, let's say, NOR gate, you can make this one, and it becomes NOR gate. Similarly, you want to make different gates and different functions, you can follow that with the given load. So here we are saying that the entire PUN, power up network, will be replaced with a single unconditional load device that pulls the output for a high output. So that is what we are going to do in this particular technique. Instead of combination of active pull down and the pull up networks, such as the consist of NMOS pull down that realize the logic function and a simple load device, which going to be replaced with the load, or you can say that with power up network, which was implementing PMOS devices. So we are going to remove that power up network, but rest of the things will be same as it was. And the name of such kind of family is pseudo-nMOS gate. So the name of the first thing which we are studying is pseudo-nMOS gate. So now here you can see that I have removed power up network and I replaced that one with some load. Definitely this load I am going to keep it PMOS because PMOS is good for transferring the logic 1. So if you want to have the better logic 1, I am going to keep PMOS here. Otherwise, like keeping NMOS will also work, but NMOS will not allow me to send this VDD exactly another side, but you will have different value. So the best part is you can take the PMOS as a load. Notably, this has been implemented with power down network, which is made up of NMOS only. That's why we are calling it pseudo NMOS. However, you might be interested in making the pseudo PMOS logic. In that case, this will be reverse. Power up network will be here with some load, and you will have the output, and here you will have some inputs. So this power up network is going to be implemented with PMOS transistors, and this is the output. So this is going to be known as pseudo PMOS logic gate, whereas the book is discussing all about pseudo NMOS logic gate. However, nobody is stopping you to make PMOS logic gate also, pseudo PMOS logic gate. You can make that, but this is going to take the lower area compared to lower. We can say that the ratio. So in that case, this might be the advantages, but depends on what particular application do you have. Accordingly, you can design one of them. But this is one of the popular one to achieve better speed. And of course, it will have lower number of transistors now. Let's understand that how it works. So here, featuring the pseudo NMOS logic gate, we have reduced number of logic, or you can say that reduced number of transistors also. Nominal output voltage is as logic 0, but not 0 volt. What exactly it meant to say is as follows. If you have, so referring to this particular circuit here, let's assume that I'm making a NOR gate. This is M1, M2, and this is M3. And this is an output. If I'm giving here A and if I'm giving here B, the output is equal to A or B bar, means it's a NOR gate using pseudo-nMOS logic gate technique. Okay, so in that case, what is happening here? Let's assume that if both A and B are 1, if both are 1, okay, I should start with if both are 0, what is going to happen? If both are 0, if this is 0, this is 0, these two transistors are off. But you should look at the upside, which is always connected to a PMOS. So M3 is a PMOS transistor, and this is 0 volt is given to here, means this transistor is always in saturation, by the way, because of the 0 volt, right? And it's going to transfer this VDD to the output. So as this is the best, you can say that this is a transistor which can transfer logic 1 from source to drain. So that is what happening over here. So when both are 0, this is going to be equal to VDD. Let's assume that there is a capacitance. So at load capacitance, VDD is going to be available at the positive plate of CL. So it's not a problem when both are 0, because if both are 0, I'm expecting the output is 1. If one of them is 0 and another one is 1, or both are 1, the output is 0. Now the whole problem starts over here. I'm expecting, note that I'm writing all these things in a binary value or the logic 1 and 0. I'm not writing in terms of voltages. So this VDD might be some other value like 1.8 volt, 2 volt, anything. And I'm writing that in a logic function. So what is going to happen over here? When this is 0 and this is 1, this transistor is on. But notably, this transistor is also on, right? This transistor is not off state. So in that case, there'll be always fighting between these two transistors, you can say PMOS and NMOS, because some voltage drop will be here. Even if I want to have, I want to send this 0 over here, I need to make sure that the resistance offered by this transistor has to be much higher than this one, right? If the resistance of M3 is more than resistance of M2, then as per the electrical property of any circuit, it will find out the lower resistance part, right? So this M2 has to have lower resistance. However, like any value you keep here, some resistance drop will be here for sure. And because of that, this node will not reach to 0 volt ever. It's impossible, because still this is in on condition. And same thing will happen when both transistors are on or one of the transistor is on. So in all these conditions, we have to make sure that the resistance offered by the power down network has to be lower than the resistance of M3. Now you must have learned till now that if I want to reduce the resistance, I need to increase W by L. So W by L of this, both the NMOS devices has to be higher than the W by L of M3. It has to be lower. so that the resistance offered by M3 is higher than the resistance offered by M1 and M2. So that is what I'm writing over here, that there is always a fight between power up network, which is a PMOS transistor connected as a diode load, and a power down network. So in this case, load device needs extra attention in terms of sizing to achieve NMH, NML, and VM. And of course, consequently, the TPHL and TPLH. Till now, you must have learned how to simulate such things, and you must have got some answer on that, right? Using Simica or CMOS inverter. So same thing, you need to do it for such a big circuit or the logic gate. Okay. Now, voltage swing is also depending on the ratio of power down network and power up network. So even though we are saying that the just some number is required over here, but you need to make sure that how much logic 0 and logic 1 do you want. So logic 1 will be always VDD in this case, but when you want to achieve the logic 0, means when both the inputs are 0 0, then okay, when in last three conditions, when one of the input is 0 and maybe both the inputs are 1, then our output will be 0. So it will not be 0, but it will be, you can say that little bit higher than 0 volt, because some voltage drop will be here because of the current flowing through this particular device, right? If it is open, then there is no problem, then there is direct connection from here to here. But here there are two connections at the single node, which is being made by resist like this. You can say that because of resistance of R3, I'm trying to connect VDD over here, and on the basis of input A and B, the resistance is R1 and R2, which are trying to connect to ground, and this is the V out. So you can never have 0 volt over here because of this VDD, right? So always there is some voltage division, as this resistance is going like this. Resistance has to be very high and these two resistance has to be very low, so that you can have this value approximately 0 volt, so that you can make this path. But you can't do that because of this path, right? So this is what we are saying over here, and you have to make some trade-off, and you cannot have ever 0 volt. You can have maybe something millivolt, like 10 millivolt, 30 millivolt, 50 millivolt, but you cannot reach 0 volt over here. And by looking at the equations, you can see that the NMOS side, which is the power down network, which is with the NMOS, it follows this condition or the current equation, which says that Kn VGS minus VTH times VDS minus VDS square by 2, right? And for other side, it's Kp VSG minus VTN VSD minus VSD square by 2. So this is for PMOS, but as PMOS is in saturation, you can replace this name as VSD sat and VSD sat, right? So this is what you can do over here. Now the whole thing is, I wanted to find out how much VOL I can achieve. So I'm saying it's approximately 0, but this is VOL voltage. If you remember, in the characteristic of an inverter or a logic gate, this is going to be known as VOH. This is going to be equal to VOL, right? So you need to find out these values. So VOH is sure that it's going to be equal to VDD, because other two transistors are off, means off, but this is going to make the path of VDD. But other case, which is VOL, we need to find out that equation. So we can find out from the fact that both the current will be equal. So current flowing through the up part, is going to be exactly equal to the same. So this is I0 and I1. So I0 and I1 are equal. provided that there is no load. By the way, if there is load, then some part will go to the load also, right? In that case, I0 is equal to I1. If I0 and I1 are equal, I0 equation is already known to me, which I have already written when the transistor is in saturation mode of operation. So this is PMOS in saturation, PMOS as a load in saturation mode of operation, whereas this one in linear. So when, if we are in three conditions which we have already talked about, like when A and B inputs are 0, 1, 1, 0 and 1, 1. In this case, we are expecting to have the output of 1 in the case of NOT. So then we have to make sure that this equation and like has to follow as written over here, where Kn is nothing but mu n Cox W by L, right? So this is already known to us. If you keep all these values and if you replace the actual gate to source and other values, like VDS is nothing but, in this case you can see the VDS, which is acting as a V out, or you can take maybe this example here. VDS is nothing but VOL, or the output voltage when the it's a logic 0. So gate to source, drain to source voltage replaced with the VOL. This is also VOL. If I am looking at VGS, means gate is connected to VDD and source is connected to 0. So you can replace this equation like this, and that is what written over here. So when you are comparing both the currents and equating VDS with VOL, you are going to have this equation VOL as ratio between ratio between WP and WN, considering the fact that all these numbers are constant. Other things are in your hand. So as you are increasing WP, VOL is increasing. Means instead of 0 volt, you would see something more than 0 volt. And that is what we already know that, right? So we have to design the things accordingly, right? Because increasing W means decreasing the resistance of PMOS. So that is what we need to make sure, that resistance offered by PMOS should be lesser than the resistance offered by NMOS. Okay. And if you look at the power consumption is nothing but whatever the low current is there, just keep over here and equate that one, is going to give you the static power. Note that here there is no load capacitance is kept, that's why it's not there. Otherwise, its CL square also should be coming when load capacitance is much higher than the parasitic capacitance offered by NMOS and PMOS, right? Now let's look at the characteristic given VTC, voltage transfer characteristic given in Rabe book, which is the example says that consider a simple pseudo NMOS inverter, means this one. Here I'm keeping A. I'm expecting here A bar, and if I'm if I'm looking at the sizing, its sizing are as follows: 0.5 micrometer by 0.25 micrometer, with the fact that the VDD is equal to 2.5 volt and this is equal to 0 volt, and this is 250 nanometer CMOS technology. This is what Rabe is following. So if you are looking at the different PMOS device sizes, you're going to see that as you are increasing W by P, resistance is decreasing, and you can see that VOL, these numbers, like this is VOL, this is VOL, this VOL is increasing with increasing the W by L of PMOS transistor. So we have to make sure that W by L has to be as low as less than 1, so that making the length longer than the width, that is also possible. And when you are doing this, you have better characteristic, and similarly you can design it for the given VT given VM and for given noise margin high, noise margin low. All these things can be done, or you can design it for the given VOH, VOL, and other things, right? So this is not so much difficult in that case. So here you can see that the number of transistors is going to reduce, not in the inverter case, but if you're looking at different transistors like different logic gates like NOR gate, NAND gate, other places you will have one transistor reduction, and as you are increasing the number of inputs, you will have drastic reduction in terms of required number of transistors. Okay. Now, along with that, as VOL is increasing with W by L of the PMOS, the current requirement is also increasing, right? Because this is directly proportional to current is directly proportional to W by L, right? So current get increase, and you can say that as current is increasing, but at the same time, the TPLH is actually reducing. If you are going upside, you can say that TPLH is reducing. For a smaller value, it was 0.69 picosecond. As it is 4, it becomes 14 picosecond. Right? So it's a trade-off, and you have to find out. You must have learned something from maybe the simulations which you are doing in Simica. So in that, you must have learned that how these sizes are affecting the TPHL, TPLH, and some of the questions were given on that. Okay, so this was all about the pseudo-nMOS logic gate. If I want to make NOR gate to this particular PMOS as a load, will be fixed. It's not going to change. I want the NOR logic, make the whole F bar over here as we were doing in the case of the CMOS logic. So implement F bar logic which says that A or B or C or oblique T. So that's going to be implemented. If you are interested in NAND gate, so you can stack these transistors one on top of another one. Okay, so this is what one of the possible thing. And here the static power dissipation of pseudo-nMOS limits its use. And this pseudo-nMOS still finds its use in large fan-in circuits. So if you are interested in finding out the large fan-in, look, you don't need to look at the, you can say that if it is a CMOS logic, you must have so many PMOS transistors in parallel. And unlike pseudo NMOS logic, where you require the PMOS transistor value much lower than the effective W by L of the whole network. In the case of CMOS logic, you need to keep the whole ratio as 2. If you remember, you need to do this one. But in this case, that is not the thing. And because of that, the input capacitance, if you look at this C in, it's actually 6, right? But in the case of this one, it might happen that this might be 0.5. I'm keeping 0.5 because effectively this is going to give me 1, and with respect to this, it's 0.5. So effective input capacitance is around 4.5 only, right? Whereas in the previous case, when it was CMOS, I need to have the input capacitance of 6. So if you want, you can, like you are ready to drive the load of maybe 6. So in this case of pseudo NMOS circuits, you can have maybe few more extra like this, or you can implement more number of inputs rather than case of the CMOS logic circuit. So you can have the large fan-in circuits. And figure also shows that the schematic of pseudo NMOS, NOR, and NAND gates, when area is most important and the reduced number of transistor count compared to the CMOS logic is quite attractive, right? So this is what the PMOS the pseudo-nMOS logic is all about. So this is the second thing which is coming under the ratioed logic, where you need to where you need to take care of all these ratios and all. Now how to build a better load? Okay, before going to the better load, let's understand few more terms. Okay, one of the term is, look, as I am saying that we are stacking the transistors one on top of another one. Means if I am doing this, if all are NMOS, if you have studied analog a bit, or if you have idea, generally we don't call this one as like we are making the series connection. We are also not saying that I'm stacking one transistor on top of another one, but I am saying that such combination as cascade. Note that this is a cascade, not cascade. Cascade is the one when one of the output of the stage is going to given to the next part. Means if you have a circuit like this, if there is circuit like this, if I am connecting this to, let's say, another circuit which is RC like this, then I can say that I am cascading inverter with the RC circuit because they are connected like this. So then it's cascade. Output of one circuit is connected to the input of another circuit, then it's known as the cascade. Whereas cascade is the one where common source is connected to the common gate amplifier, or the common source connected to the common gate configuration. I'm not going into that how it's going to be proven over here. If you want to know, then you can watch my video on analog circuit design, where I have explained how this common source is connected to the common gate amplifier. So in this case, there is a common source whose connection is given to the common gate, and I'm taking the output from here. So from here to here, the source was common, the out was taken from here. That output is connected to the common gate where this was relatively ground. So this kind of connection, we are going to call it cascade. This is one thing. So remember it. You can also call that one transistor has been stacked on top of the another one, but the real technical name is a cascade. I am defining this because we will need that. Okay, this is one thing. Other than that, there are various kind of configurations are there. One is called single-ended, one is called pseudo differential, one is called differential, and one is called fully differential. To understand everything maybe in detail, again I'm saying you should go through my another playlist of analog circuit design, where everything has been explained in detail, because these terms are related to the analog circuit designing more, but those things will be useful over here. That's why I'm defining. Single-ended is the one where one input and one output. So if there is a circuit where it has one input and one output, with respect to ground you are measuring, so then it's a single-ended. It's a if it is a pseudo differential, means there are two inputs. So input number 1 and input number 2, both are measured with respect to ground. And if you look at this, the input 1 and 2, input 2 is equal to input minus of input 1. Note that we are doing this for the fact that all these circuits are known as differential. So for all the differential circuits, inputs are going to be you can say that 180-degree phase shifted to each other, means exactly opposite. So if I'm applying input 1 as A, input 2 as B, means A is equal to B bar. This is the meaning of this if it's a digital circuit. So differential means both are 180-degree phase shifted, or you can say that they're complementary to each other. Okay. And differential is the one, like there is a actually connection between these two circuits, and these two circuits are actually disturbing each other, or you can say that because of that disturbances, the whole thing is acting as a negative feedback circuit theory, and it gives the stable output. Whereas in differential, like you must have seen such kind of symbol, it's an operational amplifier where there are two inputs, plus and minus. If I want to give the differential input, I am going to keep both of them 180-degree phase shifted with some common mode voltage. So this will be V in plus or minus, and this will be minus plus V in. So it's minus 180-degree, but the output is only 1. Then this is a differential. But if you have one more output, out plus and output minus, then it's known as the fully differential. Okay, so this was just for your information so that you can understand the wording. So now what I want to do, I want to build a better load. So if I want to build a better load, I need to use ratioed logic for sure. Ratioed logic means the pseudo-nMOS is the popular one, right? Because pseudo-nMOS is going to reduce the number of transistors. It's better than CMOS logic, where I need the same number of transistors, like NMOS and PMOS, both are needed, and the PMOS has a higher ratio. But in this case, that is not the case. So I want to like have this one. On top of that, I also have the requirement that the output has to be rail to rail. Now you understand that rail to rail means positive rail to negative rail, where positive rail is logic 1 and negative rail is logic 0. If you remember, just before a few minutes, you already understood that logic 1 is equal to VDD in the case of pseudo-nMOS transistor, whereas logic 0 is not equal to exactly 0 volt, but it's approximately 0 volt, right? That can be compensated by the W by L of PMOS, which is acting as a load. You need to keep this one as low as possible. Preferably, L has to be higher than W, right? That is what we already learned from this particular plot, right? So you can see that W by L is going in fraction, and that is only possible when you are increasing L, right? By the way, these numbers and everything has to be depend on your specification requirement. So do not make sure that every time L is higher than W. Okay, it's depending on your specifications, what switching threshold voltage you want. Maybe you are interested in switching threshold of something like this here. If it is 1.25, this is also 1.25. So you might be interested in W by L of 1 only, right? So that is also possible. So do not do the things randomly. But if you are interested to find out exactly, like your requirement says that add one, like let's make this one as 0 volt, exactly 0 volt, then like the easiest way is you can add inverter also. Look, then it will be like you can have the complete logic 1 and 0, no problem. This is also possible. But if you don't want to do that, and if you are like very much interested to do this one only, then reduce the W by L and keep it in fraction. So note that what exactly you want and what has been requirement for your specification, then you have to do. So the answer of these two things are, let's use the differential logic. Now you can understand this word. Whenever you are seeing the word called differential, means I am interested, or I am looking at the logic where it's 180-degree phase shifted, or in other word, we don't like this word because it's more looks like analog. We can say that if A I am giving, A bar also I will be giving as an input. If B I am giving as an input, B bar is also available. Means there will be two different structure. So if you know that if you are making the single-ended design, let's assume that this is single-ended. This is also single-ended. If I am giving here A and I am measuring the output, and here again giving A bar and measuring the output, this will be output bar. So this is the theory of differential, right? So I want to give input as a differential logic, and I'm going to make two single-ended circuits. And here the whole thing says that let's make such a way that the load PMOS will not be on every time. Here what is happening when we are doing this, this transistor is always on, and that's why it is asking for the current from the lower device also, and that's why they are fighting each other, and this potential is not reaching 0 volt. So I need to make sure that this transistor is going to become off sometime when it's required. So for that I have two techniques. One is called differential logic and one is called regenerative positive feedback. Let's understand that also, that how it's going to be useful. You must have seen this kind of circuit. So here if I am applying plus, output goes to minus. Look at these are the relative terms. So if this is going minus, this is becoming plus. Means if I am increasing this, this is going to be decreased, but this is going to be increased, and this is going to be decreased, and because of this is going to be increased. Look at this whole positive feedback. If you are giving here a small input, and if you leave it after certain iterations, even if you have started with smaller value like other than VDD and ground, you will end up with either VDD or ground at the output, and it will be locked because this is a positive feedback and it will not change. Means if you're starting here with some 0.3 volt, after some times you will see that because of positive feedback, what particular logic has been considered over here, that is going to be transferred, and after few cycles you will have 0.3 volt converted to either VDD or ground, right? Because this is a positive feedback. By the way, as I told you that we have started, let's say, with 0.3 volt and the supply voltage is 1.2 volt. Now what you are going to consider this 0.3 volt as logic 0 or logic 1? You might be saying that let's call that one as, so this is 1.2 volt is a VDD and 0 is this one, and you call that 0 to 0.5. I'm going to call it as a logic 0. Let's assume that. This is just an assumption. By the way, it's depending on how you are making the CMOS inverter circuit. You must be knowing that such kind of question has been given in your assignment. So let's assume that you achieved that. Now I know that 0.3 volt is here, and that is going to be considered as logic 0. If it is logic 0, output is equal to 1.2 volt. If this is 1.2 volt, the output is going to be 0. So this 0.3 volt will be erased after some time. So you can try anywhere with little bit of perturbation around the switching threshold. You will have the required output because it's a large signal device and it has very high gain, which can take you directly to VDD or to ground, right? So this thing is happening in an iteration. That's why it's known as the regenerative positive feedback. Regenerative means the output is growing up. Okay, so this is the whole theory. Okay, this is called regeneration, right? So regenerative positive feedback is actually qualifying this one as a latch circuit. You can also call it as regenerative positive feedback latch, regenerative latch, positive feedback latch, whatever you might like to call, you can call them. And the whole thing is, when you are doing this, there are many advantages of such circuit. Let's assume that, so going little bit away from what we are doing, but you might be uh, interested to know that you have done this one key debouncing circuit, where let's say I'm having a push button and I want to, let's assume that this is a digital circuit board giving the input A or giving input B. But sometimes it was happening that when we were connecting through a push button, this is not considered as one of the base solution, because the input is going like this when it's 1, or sometimes there is some debouncing is happening and then it's going up, or sometimes like this one and going like this, right? So before making the connection from 0 to 1 or from 1 to 0, there are some sort of fluctuations you are seeing, and I don't like that. So the best part to remove this one is you can use a circuit like this, which is known as SR latch, which is similar to what exactly we were made, but we made it with you can say that inverters. So here what is happening, or let's say let's make it with the inverter only. Let's say not with, I'm not going into the key debouncing completely, but key debouncing uses the NAND gates or the NOR gates. So if this is a circuit, let's assume that I'm giving an input which is like this. So as per your theory, if I'm giving directly, it might be like this, right? Because of this inverting action. But that's not true. What I'm going to do, I know that in how much value of value of frequency of these fluctuations. So frequency I know, let's assume that this is in time of fluctuations are equal to maybe 1 nanosecond. I know that 1 nanosecond and after that it's going to be settled. So what I'm doing, I'm designing an inverter whose TPHL and TPLH are much higher than 1 nanosecond. What is going to happen in that case? Even though the output is trying to reach maybe upside, it cannot go directly at the higher part, and in that case this will be treated as logic 0 or logic 1, whatever is given to that, and the output will be like this, and it's going to be latched over here, right? Yeah, so output is like this and the input will be like this. So after sometimes in the regenerative action, you won't see any of the key debouncing, and that is what we used to do, with the fact that you are adding, actually before this you can add back to back some NAND gate circuit like this, and maybe you can give it with the NOT gate, right? So both will be complement to each other, and then even if there is some key debouncing, that will be rectified by these NAND gates, right? So this is what we can do. So let's again revisit how to make the better load or the better ratioed logic and better rail to rail output. I'm going to use the differential structure, and I'm going to make the regenerative positive feedback. So this is what I'm going to do, and I am going to design new circuit, which is known as the differential cascode voltage switch logic, which has both the names. You can understand differential also and cascode also. Now you can understand this is not cascade, but this is a cascode, right? This is O. So this is what we are going to build maybe tomorrow.